Solving nonlinear inequalities is not exactly the same as solving an equation, whether it be linear or nonlinear. For example, let's take a quadratic equation versus a quadratic inequality. A quadratic equation such as x squared minus 9 equals 0, as opposed to x squared minus 9 is greater than or equal to 0. Now we're going to start with the equation because that's something we should be much more familiar with. The idea here is to employ a rule called the zero product rule, or even to use the square root property. Both are an option here. We're going to stick with factoring for the moment. This is a difference of squares that can be factored as x plus 3 times x minus 3. Now all we're doing is rewriting this side of the equation into a new form. Nothing has changed, so it's still equal to 0. We haven't in any way altered the values of that expression, we just changed the form in which we wrote it. But when it's in this form, it allows us to use a particular rule called the zero product rule. Sometimes it's called the zero factor rule or the zero product property, but in any case, it's all the same idea. It says that if a times b equals 0, then a equals 0 or b equals 0. Simply put, if the product of two or more things is 0, one of the two things had to be 0. So if we have this statement which matches the premise, we can then move to the conclusion statement that says either the first factor must have been equal to 0 or the second factor must have been equal to 0. The question is, does that work on an inequality? The answer is, unfortunately, it does not. Now, we could factor this the same way because, again, we're not changing its value. So if the value of the expression is greater than 0 or equal to 0, then factoring it doesn't change that. The question is, can we proceed from this step, where it is in factored form, to this step here where we get to separate it into two separate linear statements? Well, the reason we're able to do that is this zero product rule. So the question is, how important is that equals? If we do factor this, we're now in a situation where we have a times b is greater than or equal to 0. The question is, does that zero product rule still apply? Well, think about this. The product of two things has to be, well, let's just worry about the greater than at the moment. The equals part, I suppose, would still hold, but it's the greater than that we really need to worry about. If the product of two things is greater than 0, another way to say that is that the product of the two of them has to be positive. Well, how can we multiply two things and get a positive result? Well, I suppose both could be positive. But both have to be. It's not a matter of one it has to be positive or the other. It's both of them must be. But it is also possible to get a positive result if both factors are negative. So we get a secondary clause. Note that this has gotten much more complicated than the original. The original is very direct. If the product is 0, one of the two has to be 0. In this case, though, if the product is bigger than 0, either both must be bigger or both must be smaller. not exactly as nice of a rule, is it? The fact of the matter is that the rules that we use to solve equations are very direct because that strict requirement gives us more that we can interpret from it because it is so strict. It might be annoying to have a strict rule, but the more guidelines you have, the more rules and certainty you have, the more definitive your conclusion can be. This is very vague. It allows for a broad range of possibilities, and therefore it has a broader range of possible conclusions. Every rule that we use to solve an equation has to have some level of adaptation for an inequality, and that adaptation is usually much more complicated. As an example, imagine that this was something with 3 factors. If we're looking at a product of 3 factors, all we have to do is add one more clause. C could be 0. So long as one of the 3 things is 0, then the product will be 0. Oh, not so nice over here. If we add a 3rd factor, well, now we have to be extra careful. We have the product of 3 things coming out to be positive. That means that all 3 must be positive, or exactly 2 must be negative, and the 3rd must be positive. And if it sounds complicated, it is. In this case, we would have to say either A, B, and C are all positive, or A and B are negative with C positive, or A and C are negative with B positive, or B and C are negative with A positive. Look at how ridiculous that has gotten. Is there a better way to handle this? Absolutely there is. There is a much better way to handle inequalities than trying to deal with them through the same methods that we use for equations, because they simply don't apply. But they do apply to equations. Now, it is incorrect to set each factor greater than or equal to 0, but if we did make that mistake, we would get the same 2 values as a result. -3 from this, and +3 from that. The same 2 values we would get using the equation. Now, the only question throughout this whole thing has been about the change in symbol. While it is incorrect to use this procedure while there's an inequality symbol, it works just fine on an equation, and it's going to produce the same values either way. So here's the idea. When you are faced with a nonlinear inequality, change it to an equation just temporarily, just for a few moments. This is called the associated equation. Every inequality has one, and it is created simply by changing the inequality symbol to an equal sign. That's it. Once it is an equal sign, we're free to use the equation solving rules that we already know and we're already familiar with without having to learn new rules or adapting those rules we already know to deal with inequalities. We get to use the same rules we've been using, which is nice. It's that much less stuff to have to remember. Now, of course, at some point we are going to have to come back over to the inequality. So how do we do that? Well, the important thing is that we're going to get negative 3 or 3 regardless. The only question is, should our answer be greater than or less than negative 3? Should it be greater than or less than positive 3? Well, here's a good way to tell. We take those values and we put them onto a number line. These values are sometimes called critical values. If you go on to calculus, you'll see that phrase a lot. A very, very important topic in calculus deals with solving inequalities such as this, and you would employ the same procedure. So we mark the critical values on the number line, and what they do is they separate everything that's smaller from everything that's bigger than negative 3. And on this side, everything that's smaller than 3 from everything that's bigger than 3. So their natural dividing points is just a question of, do we want less than or greater than? For this, do we want less than or greater than? Well, there's one good way to know, really only one reliable way. Take a value that is less than negative 3 and test it out. We take a test value, x equals negative 4, and we test it in the inequality. Negative 4 squared is positive 16, and positive 16 minus 9 is 7. Well, that is actually greater than or equal to 0. What that means is negative 4 being less than negative 3 is a solution. And therefore, everything over here is a solution. Even the negative 3, remember, this does include equals. We did find that x equals negative 3 makes this equal to 0. So the negative 3 itself is also included. That can be marked with either a bracket, as we see in interval notation, or it can be marked with a filled-in dot. Both are acceptable ways of marking that if you ever have to draw the line graph. Now, we don't stop there. That might not be the only section. We've got 2 other sections, and it's possible all 3 work. It's possible that 2 of them work and the third doesn't. Maybe this is the only one that works, but the only way we're going to know is to test the other 2 sections as well. So we're going to test a value in between negative 3 and positive 3. And it can be any value in between them, but I think the most obvious and the easiest would typically be 0. 0 is a great number for evaluating expressions because most of the operations it's involved with tend to result in either 0 or the number itself. 0 squared is 0. And 0 and negative 9 is negative 9. Now, that is not greater than 0. So this section did not work. We have one more section to try then. We pick a test value over here. This time I choose positive 4. Very important that whatever you choose has to actually be in that region. Don't choose x equals 2 to test over here because this section is larger than 3. We're looking for any value that is larger than 3. 2 is not. 2 would be over here. So be very careful about what number you choose to test. 4 squared is 16. So actually, much like we had at the far left, we get 7. And that is indeed greater than or equal to 0. So this section, everything that's greater than 3, also works. And as we saw before, this includes 0, anything that's greater than or equal to 0. And through solving this, we did find that x equals 3 makes this equal to 0. So that does, again, qualify for our solution. And when all is said and done, the solution to this is negative infinity to negative 3, union positive 3 to positive infinity, as per interval notation. Now, I tend to use this union symbol in my notes, and you may see it in the textbook as well, or on some of the homework problems. I am totally fine if you were doing this work on your own with just using a comma. But when you see the union, it means this or that. That's all the union means. This U kind of shape means or. So any value that falls into this interval, anything that is less than negative 3 or equal to it, or anything that falls into this interval, anything that is bigger than or equal to positive 3. So, to solve any nonlinear inequality, start with the associated equation. Simply rewrite it with an equal sign. Solve using our familiar equation solving rules, whatever they may be, whether it's solving by factoring, whether it's using a square root property or what have you. Take those critical values, those solutions to the associated equation, and place them on the number line. They can split the number line then up into one region or two regions or three regions, or it all depends on how many critical values there are. If there are 2 critical values, we should expect 3 sections. Each section then, we test one value in the inequality and see how it stacks up. If the test value works, then the region it came from is a solution region. If the test value does not work, then this is not a solution region. And again, if a test value works, then the region it came from is a solution region. This is really, again, the only reliable and efficient way to solve nonlinear inequalities. Can we come up with rules? Can we adapt the equation solving rules that we have? Yes, but every single type of equation or inequality would require a different adaptation of the rules. And some of the rules are not quite so easy. I chose the factoring because the zero product rule is actually pretty easy to adapt if, even if it grows very large in how many situations it can occur, it still is relatively easy to understand. Things like the square root property or undoing an absolute value, not so much. So we could adapt all of those rules for inequalities, or we can use the already known and familiar rules that we have for equations. And if you ask me, that's the way to go. I've been doing this a long time, and that's how I solve all of my nonlinear inequalities. It really is the only reliable way to do it.